Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Today we will discuss propositional logic and the methods to prove the formula, validity and satisfiability. In the last session, we have already seen the propositional logic introduction. Let's see the overview of the presentation. Propositional logic introduction already in the last session we have covered. We have seen in the previous session natural deduction system and axiomatic system. In this session, we will see the semantic tableau and resolution refutation method. Let's see the semantic tableau method. In the previous methods, in the natural deduction system and axiomatic system, we have used the forward chaining approach. Means we have started from the given hypothesis and we drawn the conclusion. But in the semantic tableau method, we'll follow the backward chaining approach. So in this natural deduction and axiomatic system, we need to assume some formulas, what to eliminate, what to introduce the connectivities. We need to check out by using the formulas, the first one and the last one. But here in the semantic tableau method, we'll apply the rules systematically and we'll derive whether the formula, given formula is satisfiability and unsatisfiability. So look at here. In semantic tableau system, proofs follow backward chaining approach. In this method, a set of rules are applied systematically on a formula or a set of formula in order to establish the consistency or inconsistency, satisfiability or unsatisfiability. The semantic tableau is a binary tree which is constructed by using semantic tableau rules with the formula as a root. So here there are 9 rules are there. Let's see. A tableau for a formula alpha and beta. When it is and a symbol, then it is from the only single branch that consists of alpha and beta. When it is negation of alpha and beta, then it will be negation of alpha and beta. It is equivalent to negation of alpha or negation of beta. So when it is R symbol, then it will have the 2 new paths, one containing negation alpha and another containing the negation beta. When it is AND, then it contains only one new path. When it is R symbol, it contains the 2 new paths. Okay. The third one is alpha or beta. Already we have discussed 2 new paths. One is alpha, another one is beta. Next, a tableau formula negation of alpha or beta. Then it will be negation alpha and beta. If it is AND, then it is a single path. So, single path negation alpha and negation beta. Next, rule 5, negation of negation alpha. Then it is alpha, that is a single path only. So, same path, negation of negation alpha leads to the alpha. Next, rule number 6, a tableau for a formula alpha implies beta. When it is alpha implies beta, 2 new paths, one containing the negation, another one containing the positive. Alpha implies beta is negation, alpha, positive, beta. Next, a tableau for a formula negation of alpha implies beta, then it is negation alpha or beta, negation beta. It will be alpha and negation beta. Then it is a single path because of AND symbol, alpha and negation beta. A tableau for a formula alpha equivalents beta, then it is alpha and beta in one path, negation alpha and negation beta in another path. Then it will leads to the alpha and beta. Next, negation alpha and negation beta. Next, the last rule is, if it is a negation of alpha equivalents beta, then it is alpha and negation beta, negation alpha and beta. So here alpha, negation beta, negation alpha, beta. Okay. These are the 9 rules which are used to construct the semantic tree for the given formula. Let's see one of the example. Construct a semantic tableau for a formula A and negation B and negation B implies C. First we need to divide the atoms. So here 2. So we'll apply the first rule. So A and negation beta, because B, negation B. Here we are having AND symbol. So only one path. A and negation B. Negation B implies C for the single path. Again, we are dividing this one, taking A and negation B. So here and symbol. Again, it is a single path A, negation B. Next, this one is completed. Again, we need to check this one. Negation B implies C. Negation B implies C is negation of negation B and C. So here it will be the two new paths, negation of negation B and C. The next, negation of negation B is B and C. Okay, so here when we are having contradictory, then it is a closed, which means the complementary of pair from the starting to ending in this path we are having. There are two paths here. One is this one, another one is this one. So in this path, if you are having the contradictory pair or complementary pair, then it is said to be closed. If there is no contradictory pair, the complementary pair, then it is said to be open. Let's see. B, negation B. B comma negation B. Then it is said to be closed. I already said in this path from the starting to ending, if any of the pair having complementary, then it has to be closed. Then if you look at here, there is a C, but there is no negation C. Then it is said to be open. Let's see how we can derive the satisfiability and unsatisfiability of a formula. So here the path is said to be contradictory, that is positive and negation. Then it is said to be contradictory. In the previous example, we have seen B comma negation B. Then it is said to be contradictory or complementary. That are closed, finished whenever complementary atoms appear on the same path of a semantic tableau. Then this one is denoted as inconsistency or unsatisfiability. If all paths of a tableau for a given formula are found to be closed, then it is called as contradictory tableau. This indicates that there is no interpretation model that satisfies the alpha. If even one of the path is opened, then that alpha is this model will satisfy that alpha. But if all the paths are closed, then there is no model that satisfies the alpha. A formula alpha is said to be satisfiable if a tableau with the root alpha is not a contradictory tableau, that is, it has at least one open path. We can obtain model or an interpretation under which the formula alpha is evaluated to be true by assigning the true values. Okay, if you look at this one, C, there is no negation C, then it is said to be satisfiable by assigning the truth values here. So C equal to true and negation B equal to true, A equal to true, or C equal to true, B equal to false, A equal to true. Let's see. The formula alpha is said to be unsatisfiable of a tableau with root alpha is contradictory tableau. If you obtain a contradictory tableau with root alpha, that's said to be provable. Okay, if it is a contradictory to entire branches, then it's said to be provable. A formula alpha is said to be tableau provable, then it will be denoted like this. Alpha, if a tableau with root alpha is a contradictory tableau. Let's see. A set of formulae S equal to alpha 1 to alpha n is said to be unsatisfiable if tableau with root alpha 1 and alpha n is contradictory tableau. If it is having all the branches is contradictory, then it is said to be unsatisfiable. A set of formulae S equal to alpha 1 to alpha n is said to be satisfiable, has at least one open non-contradictory path, then it is said to be satisfiable. Let S be a set of formulae. The formula alpha is said to be tableau provable from S, that is denoted as equivalence alpha if there is a contradictory tableau from S with alpha as a root. Let's see, show that the formula, whatever we have solved that previous one, A and negation B and negation B implies C is satisfiable. So I already said that satisfiable means at least one of the path is open, then that's said to be satisfiable. Okay. So the solution has been shown in the previous example, while the other is open. One is closed, another path is open. That's why this formula is satisfiable. So here A equal to true, B equal to true, C equal to true. Otherwise we can write here negation B is true. A equal to true, B equal to false, C equal to true is a model under which R is true. We can verify this using the truth table approach also we can do. Okay, let's see. Show that A and B implies C is unsatisfiable using the tableau method. So here first we need to take and A and B implies negation A. Next again A, B. Next negation B, negation of negation A. For this negation B and negation A, because negation A is already there. So negation B, negation A. Here negation in this path, negation B and B is there. In this path, negation A and A is there. So all the branches, all the parts of this formula is closed, means which contains the contradictory pair, complementary pair. So this one is said to be unsatisfiable. If even one of the open is there, then that formula is said to be satisfiable, otherwise it is unsatisfiable. Let's see another simple method, that is resolution refutation method. So in this resolution refutation method, we'll use only negation and disjunction connectivities. Okay. So here resolution refutation is most favored method for developing computer-based systems that can be used to prove the theorems automatically. So in the previous, we have already seen the NDS and axiomatic systems, which are used to guess which rule we need to apply, which axiom we need to apply. But in the semantic and resolution refutation methods, we are having the set of rules. So we will apply those rules systematically to draw the conclusions. Okay. Here the negation of a goal to be proved. Remember this one. Whenever the alpha is given, but in the resolution refutation, we'll prove that a negation alpha. So the negation of the goal to be proved is added to the given set of classes. For example, there is a S is given and they have asked that some A or B need to be proved. Then we have to add this one to the S dash with S union and the given value. Okay, let's see. The negation of the goal to be proved is added to the given set of classes and using the resolution principle. Okay, is a refutation in a new set. We'll see in the next example. During the resolution, we need to identify two classes. One is the positive, another one is the negative. That is a complementary pair. To resolve that complementary pair, and we'll get the new atom. Okay. So here in the resolution refutation method, first we'll see the set of classes. A class which consists of the values negation and disjunction. In propositional logic, there are two normal forms. A normal form consists of the symbols, that is called as a normal form with these symbols. Okay, there are two normal forms. One is a disjunctive normal form, another one is conjunctive normal form. So the disjunctive normal form is represented as the disjunction of conjunction. So inside it is a conjunction and outside it is a disjunction. Within the parenthesis it is a conjunction, the outside it is a disjunction. Whereas a CNF is represented as the conjunction of disjunction, the opposite of a disjunction. So within the parenthesis it contains the disjunction, the outside it contains the conjunction. Let's see the disjunctive normal form. A formula which is equivalent to a given formula and which consists of sum of elementary products called disjunctive normal form. Let's see, check. So I already said in the disjunctive normal form, within the parenthesis this and symbol, outside it is R symbol. It can't be the outside and symbol. Then it will be not a disjunctive normal form. The conjunctive normal form also same as the conjunction symbol will be available inside the parenthesis. Outside should be it is a disjunctive symbol which is available in the inside the parenthesis. Outside it should be the conjunction symbol, conjunction of disjunctives. Okay, so here we can easily write CNF form given formula C1 to Cn, where each CK is 1 less than or equal to K less than or equal to N is a disjunctive of literals and is called a clause. A clause is a set of literals and with the disjunction form. Therefore, if a given formula is converted to its equivalent CNF, then the set of clauses is nothing but a set of each conjunct of CNF. Okay, the set, let's see the example. The set ARB, negation ARD, CR, negation B represented a set of classes. So, this ARB and negation ARD, all these are called as clauses. I already said that the clause is nothing but within the disjunctive form. This one. Let's see the conversion. How to convert the CNF form by using some rules, eliminating double negation signs, using De Morgan's law, using distributive law, eliminating implies and equivalence symbols. We are already have some equivalence laws. By using those laws, we can easily convert a formula into its CNF. Okay, let's see. Conversion will become clear with this example. Convert the formula negation A implies B and C and negation A into its equivalent CNF. So here we applied the equivalence law. Negation we have applied negation of A. Here negation A implies B is negation of A R B, and this one is same here. Next ARB, and we have eliminated this parenthesis. Then it is the equivalent CNF form. So here we can write the set of classes are A, R, B, comma, C, comma, negation A. Let's see the resolution of classes. For example, if you are having two classes C1 and C2, then we need to eliminate the complementary pair from the C1 and C2. Let's take the two literals L, comma, negation L are the complementary pair, and we need to take the L from the C1 and negation L from the C2, and we need to derive the new class by adding the disjunctive to that new class. Okay, let's see. Two classes can be resolved by eliminating complementary pair of literals from both. A new class is constructed by disjunction of the remaining literals in both classes. If two classes C1 and C2 contain complementary pair of literals L, negation L, then these classes may be resolved together, deleting L from C1 and negation L from C2, and constructing a new class by disjunction of the remaining literals in C1 and C2. This new class is called as resolvent or logical consequence of C1 and C2. The classes C1 and C2 are called parent classes because we have taken from those classes only. The resolution tree is an inverted binary tree with the last node being resolvent, which is generated as a part of the resolution process. Let's see one of the example. Find resolvent of the classes in the set ARB, negation ARD, CR, negation B. So from ARB, from this class and from this class, what is the complementary pair? A, negation A. We have eliminated this pair. Then we get B disjunction D. And from this B and disjunction D, we have negation A, R, D. We have taken this one. These two, we got BRD. And from these two, 1 and 2. From 1 and 2, we got BRD. Whatever new class is there, that one is 3. And the existing one, we have taken 3. From 3 and 4, we have complementary pair is B, negation B. Then we got CRD. This CRD is called as resolvent. So we can see that C or D is the resolvent of the set ARB negation ARD, comma C or negation B. So take the two classes, whatever complementary is there, eliminate those complementary pair and write the new class. And from the new class, take the existing one and the new one, compare the two and what are the complementary pair, eliminate those complementary pair and write the new class. That last one, whatever left, that is called as resolvent. Okay, so here C is a resolvent of two classes C1 and C2. Then C is called as logical consequence of the set of classes C1 and C2. This is known as resolution principle. If a contradiction is derived from set S of classes using resolution, then S said to be unsatisfiable. So if any contradiction is there, then it is said to be unsatisfiable. Derivation of contradiction for a set S by resolution method is called resolution refutation of S. Okay, let's see the next. How we can find out the logical sequence of a set of classes. First, we need to take already given set S some classes, and we need to derive the negation of the logical consequence for that and add that into S dash equal to S union the given logic negation of given logical consequence. Let's see. Using the resolution refutation concept, a clause C is defined as to be a logical consequence of S. For example, for this S, C is the logical consequence. For S, if and only if the set S dash equal to S complement equal to S union negation C is unsatisfiable, that is a contradiction, or an empty clause is reduced from the set S dash. Okay, so S dash equal to S union negation C. If it is a contradictory, then we can say C is a logical consequence of S. Let's see one example. So, using resolution refutation principle, show that C or D is a logical consequence of the set of classes. So, to prove this statement, first we need to add this one to the S as an S dash with the negation. Let's see. So, S dash equal to with S with the negation logical consequence. ARB negation ARD, CR negation B. And at last we need to add this one as the logical consequence, negation CR negation D. Now we can show that S dash is unsatisfiable. Then we can easily say that the CRD is a logical consequence of S. When we prove that negation is an contradictory to the S dash, then we can say the positive logical consequence is logical consequence to the set S. So we have written all the classes here, whatever there in the S dash, and from the first and second classes A and negation A. Then we got BRD. Next, from this new and the third one, B negation B. Then we got CRD. Next, from the new one and the fourth one, negation C. Then we got D and negation D. Then it is the closed. When it is empty or when it is something, then it is called as logical consequence. It means nothing is there. So, since we get a contradiction from S dash, we can conclude that CRD is a logical consequence of set S of classes. Okay, so in this session, we have seen the semantic tableau. In the semantic tableau, there are 9 rules are there. We have to apply these 9 rules systematically to derive whether the given formula is satisfiable or unsatisfiable. The next, we have seen satisfiability and unsatisfiability of a formulas with the example, and at last we have seen a resolution refutation. In this we have seen CNF and DNF. how to find out the logical consequence of a set of logical consequence of a set yes classes. We have seen all this in this session. Thank you.